So you should be seeing my screen. So first thing on the agenda was to talk about composite functions. Oh, and just a reminder, when you get a minute, fill out that pre-survey, and then I'll send it again, and you'll fill it out at the end, and hopefully you're feeling better about things by the end. So composite functions are really important when you're doing the chain rule. You need to be able to figure out the inside function and the outside function. So what you want to do is think about what happens to x first, and that's your inside function. For example, here we have capital F of x is the cube root of 3 plus cosecant of x. So what is the first thing that's happening to x? The first thing that happens to x is that you take cosecant of it, and then you add 3 to that. So you could actually divide this into 3 functions if you wanted to, but just saying that g of x is equal to 3 plus cosecant of x. And since we are relating this back to calculus, this is something you could easily take the derivative of. And then f of x is the cube root, or x to the 1/3. That's something you can easily take the derivative of. If we look at f of g of x, that means we would do f on 3 plus cosecant of x, which means we would take 3 plus cosecant of x and raise it to the 1/3 power. That gives me exactly what I want. So anytime you're looking for inside and outside functions and you ask yourself, have I done it right? If you can go through this process and get your original function back, you've done it right. Anytime you have a question, just let me know. So again, g of x, we have 6 times e to the 2 minus x squared. What is the first thing that happens to x? Well, the first thing that happens to x is you square it. But we can let our inside function, little g, be equal to 2 minus x squared. That's something we could easily take the derivative of all at one step. Then f of x could be equal to 6 times e to the x. Again, something we could easily take the derivative of. And then if we f g of x, that means we're going to perform f on 2 minus x squared. And that would be 6 times e to the 2 minus x squared, which is exactly what we want it to be. I like to do these next two because they look kind of alike, but they're really, really different. Anytime you have the little exponent sitting right next to the trig function, that really means cosine of 5x whole darn thing squared. So if you're thinking about inside and outside, a lot of times you think of your inside function living inside some parentheses. Well, now cosine of 5x does live inside that set of parentheses. So your first thought is, could I let cosine of 5x be my inside function? But it has an inside function, because 5x is living inside of that set of parentheses. So this time we need to start with little h of x. Then we have little g of x. And finally we have f of x, which is x squared. So we have to kind of work our way out of the parentheses. So if we f g of h, that means we're going to do f on g of 5x, which means we would f cosine of 5x, which means we would square cosine of 5x, which is exactly what we want to do. And picking the inside and outside functions is the hardest part of the chain rule. Once you get your inside and outside functions, it's pretty easy to do the derivatives on them. This time, instead of cosine being squared, we have capital I of x, cosine of 4x in parentheses squared. So you see that you have parentheses around that 4x, which makes you think, 4x is the most inside function there is. What is the next thing that happens? Well, next thing you do is the exponent. So g of x is x squared. And what's the next thing you do? Well, the last thing you do is the cosine. So the squared is in a different order this time. And if we do f of g of h of x, then we would be doing f of g of 4x, and g tells me to square it, so 4x squared, and f tells me to take the cosine of it. And that's exactly what we want. Okay, and then I did one that was just really super ugly, just to be challenging. But it's the same principle. You're just going to work your way out of the parentheses. So your insidest function, I'll write this one down, k of x is equal to secant, and then we have a square root of a natural log of x, and this whole stinking thing is to the 5th power. So I'm going to get my red pen and start here and work my way out. Natural log is the first thing that happens. Then the square root happens. Then the secant happens. Then the 5th power happens. So your most inside function, and let's see, how many did I need for this one? I needed k. Little k of x is natural log. Next thing is square root. Next thing is secant. And finally, raising it to the 5th power. So if you were using the chain rule, you kind of do this backwards. You differentiate this, then that, then that, then finally natural log. Any questions on composite functions?
No, ma'am.
Hopefully that helped a little bit. Get rid of this one. Next thing is the laws of logarithms. And in Math 171, we spend time going through and condensing log expressions and expanding log expressions. And the reason we do that is because you will use that in calculus. So it's been a while since you took pre-calculus algebra, so we'll go back over it. The log base A of A is always equal to 1, because think back to what log base A of X equals Y. Means that A to the Y power is equal to X. So log base A of A equals 1 because A to the 1 power equals A. And log base A of 1 is equal to 0 because A to the 0 power is equal to 1. So those are just things to remember. The actual laws of logarithm are the sum different, the product sum rule, the log of A times B equals log of A plus the log of B. Because if you have A to the A times A to the B, it's equal to A to the A plus B. So exponents and logarithms are partners. Their rules work the same. If you have log base A of A over B, then that's the same as log base A of capital A minus log base A of capital B, just like if you have a rational expression with exponentials, this would be A to the A minus B. And log base A of A to the n power is equal to n times log base A of A. This is the one we use the most in solving logarithmic equations, and you'll use it a lot when you get to logarithmic differentiation for a function raised to a function. The exponent can fall down. And that's because if you have A to the n power, that's the same as A multiply the exponents. If you have a power raised to a power, power raised to a power, you just multiply the exponents. So hopefully that'll help you remember those. But our goal is to be able to take logarithmic expressions and rewrite them. So we'll start with expanding. So first we'll use this product sum rule that says this is the same as the natural log of B plus the natural log minus, the natural log of C squared, because that's on the bottom. And then the 2 can fall down. Easy peasy. All these rules work exactly the same no matter what your base is. And we always take our radicals and rewrite them as rational exponents. A cubed, all of that is to the 1/2 power. So 1/2 can fall down. Then we can divide this into pieces because we have 8 plus log base 2 of a cubed. But log base 2 of 8, 8 happens to be equal to 2 to the 3rd power. And log base 2 of 2 to the 3rd power is equal to 3. So that would be 1/2 of 3 plus 3 log base 2 of a. And you could go ahead and distribute that 1/2 through there if you wanted to. So far, so good?
Yes, ma'am.
Okay. Log of 2x plus 1, and I'm going to go ahead and write this as 4 minus x to the 1/2 power, and then all of that is raised to the 5th. And remember, if there is no number down here, that means it's log base 10, the common log. So first thing I'll do is let the 5 fall down. Now I'm thinking you're probably getting pretty savvy at this by now. So let's go ahead and let the 5 fall down and divide this inside into 2 pieces. So I have log of 2x plus 1 plus log of 4 minus x to the 1/2. There is no rule for the log of 2x plus 1. You cannot divide that up into pieces. That is as simple as it gets. So we have one last step that we can do. We can do 5 times log of 2x plus 1 plus half of log of 4 minus x. And you could distribute the 5 through there if you wanted to. Now we have a big fraction going on. We have the natural log of x to the 4th, 4x plus 1 squared, all of that divided by e to the negative 5x times the square root of x plus 2. Now, by the time you've done 11 million of these, you don't want to put all those steps in because you kind of know where you're going. Everything above the fraction bar is plus. Everything below the fraction bar is minus. So this is the natural log of x to the 4th plus the natural log of 4x plus 1 squared minus the natural log of e to the minus 5x minus the natural log of x plus 2 to the 1/2. And when you've really done 2 times 11 million of them, you would have gone ahead and just let the 4 fall down in front. Let the 2 fall down in front. Natural log of e to the negative 5x, well, negative 5x falls down in front. we'll have a negative times a negative gives me plus 5x times the natural log of e, but that's equal to 1. So that just simplifies to 1. And then we have minus 1/2 natural log of x plus 2. So when you feel comfortable with it, you can start kind of combining those steps, and it's not quite so long and tedious. Now, sometimes we need to go back the other way. So let's start with something with pluses and minuses in it and rewrite it as one handy-dandy unit. So this time we're combining things, so we take that 1/3 and make it into an exponent. And then we combine those because the log of a plus the log of b is equal to the log of a times b, so a to the 1/3 times b. Easy enough. Log base 4 of c minus 2 log base 4 of d. So I see a minus sign here. I know there's going to be a fraction bar. C is going to go on top, and this 2 is going to come up here and be an exponent. So we have d squared. And there I put in all the steps. So when you're going in this direction, the first thing you do is make all of your coefficients into exponents. So log of x to the 1/2 plus log of y plus 1 cubed minus log of x plus 2 squared minus log of y to the 2/3. Now, if you want, you can go ahead and combine these two together. That makes it really obvious that they're going to be together in the denominator. So we could have log of x to the 1/2 times y plus 1 cubed minus, if I factor a minus sign out here, I would get log x plus 2 squared plus log of y to the 2/3. Now that's something I can rewrite as a product. So I have log of x 1/2 y plus 1 cubed minus log of x plus 2 squared y to the 2/3. Now I have just the log of a minus the log of b, so that's the log of a living on top of b. And again, after you've done a whole lot of them, you can probably go directly from here to here, just to be sure that everything with a plus sign is on top, everything with a minus sign is on the bottom. Okay. Let's do this one because it has a 1 in there that makes it look funny. because my goal is to write this as ln of something, just one unit. So I have 1 plus the natural log of x plus the natural log of y plus 1 minus the natural log of x plus 4. So this part is easy. It's just like the stuff we've done before, but 1 is missing a natural log. I want to rewrite 1 as the natural log. Well, natural log of e is equal to 1. And since I'm rewriting it anyway, let's go ahead and do ln of x cubed. That's as simple as it gets. And that's as simple as it gets. So now all of these have plus signs. This is just the natural log of e x squared times y plus 1, living on top of x plus 4. I don't know. Oh, I lost my plus 1 over here. I'll have to fix that in the worksheet. Yes, there should be a y plus 1. It doesn't change from here to here. Okay. Questions about laws of logarithms?
No, ma'am.
Awesome. Well, since we're thinking about logs, let's do some log equations, because part of what you're going to be doing is taking derivatives and setting them equal to usually 0, but every once in a while another number. So let's solve some log equations. Solving log equations depends on what we talked about just a moment ago, the fact that if log base a of x is equal to y, if y equals log base b of x, then b to the y equals x. So we just get something into y equals log of something and then rewrite it using exponential form. And if the log base a of x is equal to the log base a of y, x has to be equal to y. And you always have to check your solutions back in the original equations, because you can only take the log of positive stuff. You cannot log 0 or anything negative. So that's why we have to be able to rewrite things as one handy dandy log unit. So I start here with log of x plus log of x minus 1 equals log of 3x plus 12. So step number 1, I rewrite this as log of x times x minus 1 equals log of 3x plus 12. Now I have this first situation here. I have log base 10 of x times x minus 1 equals log base 10 of 3x plus 12. So x times x minus 1, which I'm going to go ahead and distribute, has to be equal to 3x plus 12. And now we're back to what we learned last week, solving polynomial equations. I have to bring the 3x over here. Subtract 12 from each side. So I have x minus 6 times x plus 2 is 0. Let's see. Inners gives me -6, outers gives me +2, last gives me -12. So I get two potential answers, x plus 6, x is equal to 6, and x is equal to -2. These are only potential answers because I always have to go back and check in the original. So can I plug 6 in here? Yeah. 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 You get the happy face of approval. Can I plug -2 in here? And as soon as I say no, it gets the big X mark of death, doom, and destruction. So we got one answer for that one. Let's look at the next one. This one, I have a 1 sitting on one side. So I'm not going to be able to write this as log base 4 of one thing is just equal to log base 4 of something else. I'm going to have to use the other method where I rewrite it as an exponential. But this is log base 4. I have 2 plus log base 4 of x plus 3, so it's going to be 2 times x plus 3. And I'm going to move this over here just because that way I can draw my little arrow, and I like drawing my little arrow. 4 to the first power has to be equal to 2 times x plus 3. And now I have a super simple thing to solve. Yay. And then I subtract 6 from each side, so -2 is equal to 2x, -1 is equal to x. So then I have to go back and see if it works. Again, this is just a potential. We got to decide if we want to slide right or slide left on it. We check it back in the original, and yeah, we can plug -1 in there, and we'll still be taking the log of a positive thing. So it gets the happy face of approval. Again, we have log of this plus log of that equals a number. So we're going to have to do writing it as an exponential. And we remind ourselves that if there is no base showing, that means it's log base 10, the common log. And I'm going to go ahead and write this as t plus 3 times t equals 1. So 10 to the first power is equal to t squared plus 3t. So let's get everybody on the right-hand side. T squared plus 3t minus 10. Product is -10. Sum is +3. That means +5 and -2 will work for me. And then I have to go way back up to the tippy top. I have to plug it into the log of t plus 3, and I can't even put -5 into that, so bye-bye. 2, yeah, I can do log of 2 plus 3, and I can do log of 2. So one good answer, one bad answer. This one, we're going to have a rational equation to solve because I have the natural log of 4x squared over 3x is equal to 2. Well, the laws of order of operations tell me that I can do what's inside the parentheses first. So I can rewrite this as 4x over 3. That makes my life even easier. When we have a natural log, the base is e. So there's a little invisible e sitting there. E squared is equal to 4x over 3. So 3 times e squared is 4x, and 3e squared over 4 is equal to x. And again, you would have to check to be sure, but everything here is positive, so you plug it in and life is good. Questions?
Nope.
Okay, one more. And I'm going to go ahead and write this as log base 3 of t plus 1 over t minus 1 equals negative 2. So draw my little arrow. 3 to the negative 2 power equals this over that. Well, that's a negative exponent. That means the same thing as 1 over 3 squared equals this over that, which is the same thing as 1 over 9 equals this over that. I like to cross multiply. It makes me happy. So t minus 1 is equal to 9t plus 9. Let's bring all my t's over to the right-hand side just because I like positive stuff. So I subtract t, I subtract 9. So I end up with minus 10 over 8 is equal to t. If I try to plug that into my original over here, because that's where we go to plug it in, I end up with a negative thing. I got a bad answer, and it was my only potential answer. So there is no solution to that equation. Questions about solving log equations?
No, ma'am.
All righty. Then let's go on to the last topic of the day, which is solving trig equations. And again, this is going to come up because you're going to be asked to figure out where a function has horizontal tangent lines, or where the slope of the function is equal to the slope of a certain line or another certain function. And you'll have to take the derivative and set it equal to a number. So first thing you do is isolate the trig function, and all the examples I have here today are from the unit circle. So you should be able to get nice, friendly, exact answers for them. They aren't always. And if they're not, then WebAssign will warn you and tell you you can round it to a certain number of decimal places, or you can just leave it as arc cosine of something. So we isolate our trig function. We have 2 cosine of t equals -1, and I'm given a certain interval that I want my solution. I want my solution to live between 0 and 2 pi, because we know how trig functions are. They repeat themselves over and over, so you are going to have infinitely many answers. So you may be asked to give all the answers. You may be asked to give all of the answers in a certain range, and you need to be able to know how to do both. So first thing we'll do is cosine of t equals -1/2. So just isolate your trig function. Now, you have your calculator, and good, this one's in radian mode. I could just do inverse cosine of -1/2. And it gives me a decimal number. What if WebAssign wanted an exact number, an exact answer? Well, hopefully you remember your unit circle. Cosine is equal to 1/2 anytime you have a 3 on the denominator of your pi. So pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And cosine is negative anytime we're to the left of the y-axis. So cosine of t is equal to -1/2 when t is equal to 2 pi over 3. And if you needed all of the answers in the whole wide world, you would need to add 2 pi k to that, where k is any integer, or 4 pi over 3 plus 2 pi k, where k is any integer. Since you only are interested in the answers living on the unit circle in this particular example, then you only need the 2 pi over 3 and the 4 pi over 3. Hi, Kennedy.
Hello.
So, more incentive to memorize that unit circle. I'm recording this, Kennedy, so if you want a copy of the tape, just shoot me an email and I'll send you a link to the video. 2 sine 5x equals square root of 3. So we need to solve 2 sine 5x equals square root of 3. And again, we're given an interval over which we want the solution, from -2 pi to 2 pi. So I'm going to isolate my trig function. So now I think about my unit circle again. Sine is equal to square root of 3 over 2. Hey, it's the exact same thing as when cosine is 1/2. It's at the pi over 3 things. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And I need to know the ones where sign is positive. And sign is positive when it's above the x-axis. So it's those two, pi over 3 and 2 pi over 3. So 5x is equal to, let's start with just pi over 3 plus 2 pi k. But I don't want to know what 5x is. I want to know what x is, and I can't have a k because I'm given an interval over which I want the answers. So I divide this whole thing by 5. So x is equal to pi over 15 plus 2/5 pi k. Now I have to add 2/5 to 15 and see how many I'm going to find that are in this interval between negative 2 pi and 2 pi. I'm going to rewrite this as pi over 15. I need a common denominator so I can add and subtract. So that would be 6 over 15 pi k. So for this one, I'm going to start with pi over 15. I add 6 pi over 15. That gives me 7 pi over 15. I add another 6 pi over 15. That gives me 13 pi over 15. I add another one. That gives me 19 pi over 15. And I'm going to stop as soon as I get to 2 pi. So when I add another 6 pi over 15, I get 25 pi over 15. So that's all the ones between 0 and 2 pi. Now I need to subtract so I can find the ones between negative 2 pi and 0. There are going to be a boatload of answers to this question. So we have pi over 15 minus, so it would be minus 5 pi over 15, minus 6 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 pi over 15. Now we notice we had 5 here multiplied by x, and we have pi over 3 plus 2 pi k. We're going to end up with 5 answers for every interval from 0 to 2 pi. So I got 1, 2, 3, 4, 5 answers plus the 5 negative answers. I'm going to get the same darn thing when I look at 2 pi over 3. 2 pi, 5x equals 2 pi over 3 plus 2 pi k. So divide everything by 5. X equals 2 pi over 15 plus 2/5 pi k, which is the same thing as 2 pi over 15 plus 10 pi. No, again, 6 pi over 15 k. And you're going to do a whole bunch of adding. I don't think you need to see me do all that adding. But you'll end up with 10 more answers. Questions? That was a lot. Looks like my answers went off the edge of the page. There were so many of them. Okay. The next one's my favorite because it's super easy. Cosine of 3x equals 2 has absolutely no solutions because we know that cosine of x lives between -1 and 1. If you graph it, it looks like that. Never gets higher than 1, never gets lower than -1. And if we do cosine of 3x, it still never gets higher than 1, never gets lower than -1. So that one was easy peasy. Let's do one with a tangent in it. 8 times tan of 2x. And let's go ahead and add 5 to each side. So tan of 2x is equal to 1. Now, maybe you remember where tangent is equal to 1. Maybe you don't. It would be where sine of 2x over cosine of 2x is equal to 1. So where is sine equal to cosine? So hopefully you can remember one of these two things. Looking at our unit circle, we know that sine and cosine are both square root of 2 over 2 at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. They're both positive in quadrant 1. They're both negative in quadrant 3. So tangent is equal to 1, tangent is equal to 1, tangent is -1, tangent is -1. So tan of 2x, and tan's pretty cool because even though I have two answers in the interval between 0 and 2 pi, I can just write it as pi over 4 plus pi k because it cycles every pi units instead of 2 pi. So that should be 2x is equal to pi over 4 plus pi k. So x is pi over 8 plus pi over 2k. So x is equal to pi over 8 plus 4 pi over 8k. And I need to find the answers that live between -pi halves and 3 pi halves. So I just subtract and add until I get them. And I end up with -3 pi over 8, pi over 8, 5 pi over 8, and 9 pi over 8. And you just go, if you added another 4 pi over 8, you would get 13 pi over 8, which is bigger than 3 pi halves. Questions so far? Okay, I got one more for you. This one looks kind of like a quadratic. So just like you would do with a quadratic, you're going to factor. So 2 sine of x, sine of x. If you need to, you can let u be equal to sine of x and just factor it with u's in it. But this one's so easy to factor. We got to have 2 sine of x, we got to have sine x, we got to have 1, and we've got to have 1. We just need to figure out where the pluses and minuses go so that we end up with that minus sine x in the middle. If I put my minus sign here, then I'll have minus 2 sine x plus 1 sine x, and that gives me exactly what I want. So now I have two little baby equations to solve. And move this because I write big. So 2 sine x equals -1. Let me go ahead and put the steps in. 2 sine x equals -1. Sine of x is -1/2. And then over here, sine x minus 1 is 0. Sine of x equals 1. That one's easy because I only need my answers on the interval from 0 to 2 pi. So there's only one place that happens. There's two places where sine is equal to -1/2. So again, I think back about that unit circle. Sine has the short leg at anything that has pi over 6. So pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And sine is negative when we are below the axis, so these are the winners. So set it equal to 0. Sometimes you'll have to factor. Sometimes you'll get one good answer. You'll have to throw some out. Sometimes you'll have to find all of the ones in a certain range. Questions? I am going to throw that survey up in the chat box for you. And if you don't mind filling it out again for me, I appreciate it. Let me know if there's anything that I can do that helps, any questions that you have, any topic you want me to cover. I'm glad to do it.